Good afternoon. I'm David Nuremberg, the director and Leon Levy professor here at the Institute for Advanced Study. I'm very sorry about the weather. You're about to learn that we can actually pry information out of black holes, but we cannot apparently affect our own climate. I'm pleased to welcome you all to this evening's panel, this afternoon's panel, and to welcome our board of trustees who is with us in person for the first time since 2019, which makes this a very special occasion to think about our community as a whole and the presence that makes our community so special. And why did I think that this would be the perfect panel to celebrate that? Well, it has a lot to do with my own very recent entry into this community. And as part of that entry, I talked to all of the faculty, and I went and talked to Edward Witten. And I asked him, many of you have probably felt trepidation when speaking with a great scientist. I asked him what he was working on, and he said he was currently very interested in quantum information and gravitational theory, the intersection. Well, I was too afraid to ask him to expound on what he meant, but I did what we all do at the Institute. I bumped into someone at tea. I bumped into Ahmed Almheiri at tea, and I asked him, would you have lunch with me and explain to me this field? And he did. And it emerged to me as a very intricate story about interrelations between a very small number of people, from the most senior to the most junior, doing vital work that transforms what we can know in the context of a small community, the Institute for Advanced Study, not only the Institute, but the Institute being the place where a few people can make sense of something so difficult that it can revolutionize science. So that's why I thought this was the perfect panel. And there's many other reasons we could think of this panel as exemplary. I noticed that we have Juan Maldacena, we have an Argentine, a Brit, an Indian, United Arab Emirates. Science is international, and at a time when borders are being put up against the free flow of scientists all over the world, it's good to remember that this kind of science requires all of us, the global collective intellect. So, tonight we have 4 researchers, and I want to first mention the Carl P. Feinberg Professor at the Institute for Advanced Study, Juan Maldacena, who has made significant contributions. Everyone on this stage has made significant contributions, but Juan to string theory and cosmology, the relationship between quantum gravity and quantum field theories, and the deep connection between black holes and quantum field theories. Juan's 1997 paper on ADS CFT correspondence, which now I'm talking about something I don't know anything about, you can probably tell, which links anti-de Sitter spaces and conformal field theories, is one of the most widely cited articles in the field of high energy physics and has become a major topic in theoretical physics. And in 2013, he transformed the field of physics again with the claim that Einstein-Rosen bridges are mathematically equivalent to entangled particles, sometimes called Einstein-Podolsky-Rosen pairs. Juan is a winner of numerous awards, including the Galileo Galilei Medal, the Prange Prize, the Albert Einstein Medal, the Lorentz Medal, the Dirac Medal, the Breakthrough Prize. He's also the recipient of a MacArthur Fellowship, Packard Fellowship, Sloan Fellowship, and I could go on and on. Distinguished visiting professor Subir Sachdev is Herschel Smith Professor of Physics at Harvard University. He studies the diverse varieties of quantum entangled states of modern materials. His work connects to modern developments in quantum field theory and quantum gravity, in addition to experiments on high temperature superconductors. Recently, his theories contributed to the first observation of a new state of matter known as quantum spin liquid by the Harvard Quantum Initiative. Subir is also the winner of numerous awards, including the Lars Onsager Prize and the Dirac Medal for his field-shaping insights. And then current junior visiting professor and IBM Einstein Fellow Geoff Penington is conducting studies at IAS, visiting from his home institution, the University of California at Berkeley, where he serves on the faculty. He works on the connection between quantum information theory and quantum gravity. You start to see a pattern. In particular, he's interested in understanding how information escapes from evaporating black holes. Geoff was recognized, along with Ahmed Almheiri, our final panelist, by the Breakthrough Prize Committee with the 2021 New Horizons in Physics Prize for, quote, calculating the quantum information content of a black hole and its radiation. This distinguished prize is reserved for early career researchers. Ahmed has been a member at IAS since 2017, working at understanding the connections between quantum information theory, quantum field theory, and quantum gravity. In 2012, he was co-author of a paper which introduced a concept called the black hole firewall paradox, an influential theory which addresses the information problem. Since then, he's continued to make advancements in our understanding of what happens inside black holes. So to begin tonight's panel, I'd like to invite Juan Maldacena.
So I will tell you about developments about black holes that happened before the recent developments that you'll hear in the next three talks. So let's see why this doesn't work. So first, a very quick summary. So Carl Schwarzschild found that general relativity, the Einstein theory of gravity, predicts black holes. Einstein himself was confused. He thought that this wasn't the case. So, and then it was shown that they are actually unavoidable given the equations of general relativity. Oppenheimer, the former director here at the IAS, was instrumental in showing that. Now, not only that, but then Hawking showed that black holes are actually not black. So he showed that they emit some radiation, then they can be red or white. It's hard to see the white one. And then he also said that they might imply that quantum mechanics and gravity are not compatible with each other. Now, black holes are first and foremost a great distortion in the flow of time. So let me try to explain that. So this person, Schwarzschild, he found the space-time geometry around the spherical massive body. So he considered the star, and he solved Einstein's equations outside and found the full geometry. This geometry has 4 dimensions of space and time. And this geometry tells us many things, but in particular, it tells us how time flows and how the flow of time changes. So far away, clocks flow at a certain speed. And when you are close to the surface of the star, they flow a little more slowly. Here, due to somehow the Zoom transmission, they don't flow very smoothly, but when you get close, when you take the same star and you make it even smaller, time flows even more slowly, and a person here would feel even a larger weight. So here we're taking the same star with the same mass and making it smaller and smaller. And then eventually, when it gets smaller than a certain radius, which we now call the black hole radius, something very weird happens. So someone sitting there would be feeling an infinite weight, and in addition, time would not flow. So it looks as if time gets to stand still. And this is what troubled Einstein. He said, well, surely you can't have something like that. So a star can never become as small as that. But it was shown that no, the star can be this small, and not only that, but the geometry can continue behind the horizon. So just to explain how that happens, I show you this by producing some diagrams, which we call space-time diagrams. So these are diagrams when we try to represent the geometry of space and time, in this case, 2-dimensional. So we have 1-dimensional space and 1-dimensional time. Each point on this space is an event, something that happens at a particular space and at a particular time. And someone sitting at a fixed position would be described by a line. Someone moving with some velocity would be described by a line that is now tilted. So this is moving to the right. So at different times, the position is different. And they cross at a particular time and a particular position. So that's the event when they cross. That's the point where they cross. A light ray, again, follows a straight trajectory, which in this diagram is, let's say, at 45 degrees. We've set the speed of light to 1. And finally, if you have someone who's moving with constant acceleration, you would follow a trajectory of this kind, which will approach a particular light ray. And a person who's following that trajectory would feel a force pushing that person to the left, to that side of the screen. Okay. So the force pushing the person to the bottom of the rocket that is pushing, the rocket is pushing to the right side. So that's all in flat space. Now, the idea is that an observer who's sitting at a fixed position outside the horizon is described by a geometry which is similar to the geometry of flat space, but looked by an accelerated observer. So we have this accelerated observer, and we have the light ray, and that's how the geometry near the horizon feels. And the fact that this person feels an infinite force is because it's getting very close and it's accelerating very, very fast. Okay? But you could also choose not to accelerate, and you could choose to fall freely. And so if you have someone who's falling freely, so they can fall freely as they just move, they're just moving and existing in flat space, so they can cross this horizon without any problem. So they don't feel anything special when they cross the horizon. But then as they continue going into that region, they feel bigger and bigger gravitational forces that tear them apart. And eventually they go into a region with infinitely big space-time distortion, which we call the singularity. Singularity just means that we don't know what's going on there. Okay? But what we know is that they will die even before they get to the singularity. Okay, not good to go there. So you should think of this region behind the horizon as a little bubble of collapsing universe. So inside each black hole, there is a region of the universe that is collapsing, a big crunch inside each black hole. And someone who falls in there dies. Okay, a few words about real black holes. So now we are in a time where it's a golden age for astrophysical observations of black holes. And I could not give a talk about black holes without mentioning at least one of them. So I'm going to mention just one of the recent observations. So this is a field of galaxies. So, well, there are stars and there are some galaxies. And we're going to concentrate on that particular galaxy over there. And this galaxy has a peculiar feature that as I start zooming in, you might start noticing it. Perhaps you notice it now. So there is a big stream of particles and coming out from the center of the galaxy. This is very, very big, much bigger than the size of the galaxy. So there is something very powerful going on in the center of this galaxy. And people had theorized that what goes on in there is that there is a big black hole and matter falls into this black hole, and some of the matter sort of splashes out and comes out in this way. And recently there was a very nice picture that was taken with a very powerful radio telescope that managed to resolve the region very close to the black hole. So this is light coming from the matter going around the black hole, and the black hole would roughly be more or less this size here in the middle. And it has a characteristic shape, which is what you would expect as if there was a black hole. The size of this black hole that is in there is the size roughly of the solar system. So it's a very big, supermassive black hole. And there is a rumor that they will take a similar picture of the black hole in the center of our galaxy. So now that was one of the experimental aspects or observational aspects. Now we'll turn back to theoretical aspects and we'll remain there for most of the talk. So we will include now quantum mechanical effects when we consider a black hole. And as we said, black holes are not always black. And that's because black holes emit this radiation that is called Hawking radiation. They have a temperature that you can compute. It's due to quantum mechanical effects. I think Geoff will mention them a little more. And the temperature of a black hole increases as the size of the black hole decreases. So as you make it smaller, it gets hotter, redder, and if you make it even smaller, it looks white. Unfortunately, it looks like the background in the screen. Now, for temperatures of black holes of various masses are as follows. So if you have a black hole of the mass of the sun, the temperature is very, very tiny, too small for it to be measured. So we cannot measure this effect with these big astrophysical black holes that exist out there. However, you could theoretically imagine a black hole that was smaller, that had the mass of a continent, for example. It would have roughly the size of a bacterium, and it would look, it would have a temperature of the order of the temperature of the sun, and it would look white. Okay, so there you have a white black hole. This effect is so surprising that even the name of the black hole was chosen wrong. Now, this temperature is a little funny for the following reason. So in physics, we are used to thinking about temperature in terms of the microscopic motion of the constituents. So if we have a hot gas or a cold gas, the hot gas is hotter because the molecules are moving faster than the ones in the cold gas. In other words, heat is due to the microscopic motion of the constituents of matter. Now you can wonder, in the case of the black hole, what are these moving constituents? And there are various ideas. We cannot answer this very easily. However, something we can answer easily is how much information do we require to describe this motion? And we can answer this easily because that can be done using the laws of thermodynamics and statistical mechanics. So there is a quantity in statistical mechanics, which is called the amount of information, or sometimes called entropy. If you never heard about it, don't worry about it. So it's something that measures the amount of information that you would need if you were to somehow take a picture of that moving gas. So if you took a picture and you say, how many megabytes do you need to describe that picture? That's this number. And this number is the area of the black hole divided by a very tiny length scale that is a combination of the constants of nature, G Newton, the Newton constant, and the Planck constant, and the speed of light, and so on, which works out to be a very tiny distance, very, very, very small, much, much smaller than any distance we can physically observe. But because this distance is so small, this information or entropy is very, very big. So black holes need a lot of information in order for us to describe them. That we just derive from the laws of thermodynamics. Now, these results have inspired an influential hypothesis, something that we have called the central dogma of quantum black holes. Dogma in the sense of assumption. So it's an assumption, and it's an unproven assumption if you start with the laws of gravity. And that's the idea that black holes, if you look at them from the outside, you can think of them as described as a quantum system with a number of constituents given by the area, number of states given by the area. Or said in a slightly different way, the idea is that if you want to describe a black hole from the outside, the black hole could be simulated by a quantum computer, which has a number of qubits that is given by the area. So the memory of this computer should have a size which is of order the area. Okay? That's the size of the hard drive that your computer would need. It's very, very big, much bigger than the size of any quantum computer that exists, and even any classical computer that exists, and so on. Now, we have some concrete theoretical quantum theories which are supposed to describe these black holes. So some more concrete hypotheses, and Subir will describe one such model that has many aspects in common with charged black holes. So he'll describe a more concrete quantum system. But not everyone was agreed with this point of view. So there were skeptics. And Stephen Hawking was the most famous of those skeptics, that there is a reason why this picture, this idea that I just presented, this central dogma, was actually not correct. And Geoff will do his best to explain that position. He will try to explain Hawking's position. So as another British person, perhaps. And in Ahmed talks, you will hear about the resolution or the reason why the previous argument by Hawking, we think it's not correct, and we now think that indeed that central dogma is probably correct. Okay, thank you.
Thank you, Juan, for that very nice introduction. I knew very little about black holes until a few years back, and it's through listening to people like Juan that I've ventured to talk about them a little bit today. So my own interests are not so much in black holes per se, but in a central ingredient of the theory of black holes that Juan was presenting, which is quantum entanglement. So I'll introduce the basic ideas of quantum entanglement and discuss how they apply not only to black holes, but to many other things in laboratories around the world. So from Juan, we learned that black holes have an entropy and a temperature, and the entropy, meaning the number of degrees of freedom, is proportional to the surface area. To complete the list of things that you need to know, there's one other thing that I'll add, and that black holes have a amazing ability to just very quickly become black. So if you throw a star into it, it'll very quickly become a slightly bigger black hole, which is a perfect sphere. And the time it takes to that, you can relate to the time it takes for the black hole to reach thermal equilibrium, because the perfect spherical shape is in thermal equilibrium. And it turns out there is a fundamental speed limit on how fast things can equilibrate. And the black holes seem to be exactly at it. So then a question becomes, how can, if you want to now make a quantum computer that's going to simulate a black hole, meaning, if you got a bunch of qubits, these are ones and zeros, which are behaving quantum mechanically, and you couple them together, the theory tells us if you couple them just right to an outside observer, that these qubits will look like a black hole. So we can ask, well, what kind of quantum computer do we need? What are some of the features of this computer? Well, Juan already told you that the number of qubits, the number of ones and zeros you're going to need is very, very large, but it's proportional to the surface area of the black hole. And to have the other feature that they relax to thermal equilibrium so quickly, you need long-range entanglement. You need something that's extremely strongly entangled. So what is quantum entanglement? Well, the idea of quantum entanglement, well, later on, I guess, often referred to spooky action at a distance. And this spooky action phrase has often been ascribed to Einstein. And I thought that was a fake story until Ahmed went to the Institute library and found that he actually used this word in a letter to Max Born. Okay, there it's in German. I won't try to pronounce that. But Einstein said, I cannot seriously believe in quantum entanglement because the theory cannot be reconciled I can't read it, with the idea that physics should represent a reality in space and time, free from spooky action and a distance. So what he's referring to here is a strange feature of quantum mechanics that when two particles or two qubits are entangled, if you perturb one or look at one, it immediately affects in a spooky manner the other one. Now, the idea of spooky action actually is very old. It was accidentally discovered, but not in this language, by Auguste Kekule, who was a chemist in the 19th century thinking about the benzene molecule. And I found in Wikipedia this quote, what happened? So Kekule spoke of the creation of his theory. He said that he discovered the ring shape of the benzene molecule after having a daydream of a snake seizing on its own tail. So what was this picture of benzene molecule? So benzene has 6 carbon atoms, and just focus on a single electron on a carbon atom. Now these electrons like to form covalent bonds represented by this ellipse. So here in this covalent bond, you have one electron which is spinning one way and the other the opposite way, or vice versa. And this, of course, Kekule didn't know, but he knew that the electrons like to form this bond. But if you have 6 of them in a ring, there's no symmetrical way for them to form this bond. You can either choose this one or that one. Oops, I don't know why you can either choose this one or the other one. Oops, there we go, sorry. And the answer, Kekule said, well, it's resonating between the two. Somehow he had this picture that these two distinct physical states are both present at the same time, and the molecule is oscillating between the two. Well, in quantum mechanics, we say that it's really entangled. These are 6 electrons that are entangled, and they're in both of these states at the same time. So that's a very simplest example of entanglement, which occurs in something as simple as the benzene molecule. Okay, but we now want to talk about not just 2 of these, not just 6 electrons, but really a very, very large number of them. So I can say I had this idea, my spooky dream, based on the Indian game of snakes and ladders, where you just imagine that the snake is entanglement and it can go from anywhere to anywhere. Anyway, okay. So then I'll introduce a very simple model, now called the SYK model, which teaches us a lot about what happens when you have many electrons all entangled with each other. So imagine there's a set of random positions on which electrons can reside, and you put a few of them in some of the positions. And now these electrons are going to move around, and you want them to move in a way that they entangle with each other very strongly. So for example, you can imagine this pair of electrons moving from here to there. And this will happen in the quantum theory by at some rate, and that rate is characterized by a complex number which describes the quantum evolution of the many particle state. So there's lots of possible motions here, each with, where you take a pair of particles moving from those two sites to those two sites and so on. And this, it turns out, an interesting model, but it's extremely hard to solve. But what we realize that you can solve this model if you just assume that each of those processes has a random number associated with it. So this is one of those instances that happens occasionally in physics and computer science too. When you make a problem random, it somehow becomes easier to solve. So we could solve this problem and then really understand in a simple case what happens when you have many, many particles entangled with each other. Okay. All right. So it turns out that this type of model has entanglement at all scale. It has a scale invariant structure, and the dynamics is sort of universal. And it turns out to then describe not only electrons moving in a metal, what's called a strange metal. It appears in the compound called yttrium barium copper oxide. But if you take a different view of it in a dual set of variables, it describes certain types of black holes. So there's this amazing connection between motion of electrons with lots of entanglement in a little crystal in the lab to what's happening with quantum entanglement on the surface of a black hole or inside a black hole. So here's an example of this material I just mentioned, yttrium barium copper oxide. It looks like that. And if you dip it in a bit of liquid nitrogen and set it over magnets, well, it's a superconductor, and it's an ability to just float and carry current without dissipating any energy. Of course, at that point, it's heated up. If you hadn't heated up, it'd keep going forever. So these are very useful materials put to many uses. Probably the most exciting is this company called Commonwealth Fusion Systems in Massachusetts, which thinks it can use these new materials to make clean fusion energy. But all right, so this is just their own promotional blurb. I'm not a recommendation to invest in this company. All right, so I've told you a little bit about this strange metal, this strange material, like by BCO, which has entanglement at all scales. Why does it describe a black hole? So here I'll just say a few things about that and conclude. So here I want to focus on a particular type of black hole, which there's a net charge. And for these black holes have the feature that if you're falling into them, if you were unlucky enough to fall into this black hole, it would feel to you as if the universe has become one-dimensional. There will be only one space dimension, and the transverse directions would disappear, would decouple, as we say. So in the end, when you're unlucky to be falling into a black hole, but you're lucky because you're living in a much simpler universe. You're living in a universe, there's only one space dimension. And then we can apply some of the dogmas that Juan discovered to this much simpler universe with only one space dimension. And one of the things that Juan told us, that if you want to make a quantum computer, that quantum computer should be in one lower dimension. So in this case, you're in one space dimension, so your quantum computer should be in 0 space dimensions. So do we know a quantum computer in 0 space dimensions? Well, that's exactly the SYK model. And so there turns out to be a rather explicit connection between the dynamics of these entangled electrons and the dynamics in this very peculiar type of black hole, which probably doesn't exist out there. But it's a very useful playground to test these theories.
Okay. Awesome. So yeah, I'm just gonna talk a bit about why Hawking thought that the black holes were so problematic for quantum mechanics and gravity. So this is the black hole information problem. Some of you may have heard of it. It's been a fairly famous part of physics for the last 50 years or so. But before I start talking about black holes, we've heard a lot about them already, but let's just start with something a bit more simple and down to earth, namely an egg. And I'm going to take this egg and I'm going to drop it. And what's going to happen, it's going to hit the floor, it's going to splatter. Unsurprising. Now let's do something that might be slightly more surprising for some of you. We're going to stop time. Let's just imagine we can do that. We're going to take every particle, one by one, that makes up this splattering egg, and we're going to reverse all their velocities. And then we're going to start time again. What do we think is going to happen? Well, turns out the answer is something that may look a bit weird, but it's this. All the particles are going to splatter towards each other. They're going to coalesce in exactly the right way that the egg will magically pop into a solid object. It will get a load of momentum from all that momentum coming together, and that will cause it to pop up into the air. Okay, it's the exact reverse. That was literally the video of the egg splattering playing backwards, as I'm sure you all realized. But that is actually what would happen if you did that process, modulo some subtleties about particle physics that I won't go into. So the laws of physics at a very fundamental level are reversible. What you can evolve forwards, and then you can evolve backwards and get what you started with. And that leads to a very profound thing, which is that if you have information in the state of your universe at some time, and then you look at the universe at a later time, you can always find that same information. It might be less accessible than it used to be, but it will always be there because we can, in principle, always evolve backwards in time. So let's say I had a book. And let's say I want to destroy the information in this book as permanently as possible. You know, maybe I read the book and hated it. Maybe I read the book, really liked it, and I'm embarrassed about my choice of reading. Who knows? But I want to destroy this book. So how would I do it? In practice, I might do the following. I take the book and I shred it up, and it's in tiny pieces. And probably no one's ever going to find out what book I was reading. But if the NSA decides the thing they really want to spend their budget on this year is figuring out what book I was reading, they can probably do it. They can piece together all the little pieces, match up them microscopic details, and they can work out what I read. Okay, let's step our game up a bit. I'm going to take the book and I'm going to burn it. It's now a pile of ash and some slightly hotter air than we had before. And at this point, even the NSA is not figuring out the book I'm reading. We're all safe. In practice, you do not need to worry. But in principle, the information in the book is still there in the complicated structure of the states of the air molecules, the light and heat that got emitted, the state of the ash, all that stuff, in principle, tells you the words that were written in the book, just in some incredibly complex, impractical way. Okay, we've got to step our game up again. I'm going to take this book. I'm going to fly off to the nearest black hole in my spaceship, and I'm going to throw the book into the black hole. As we saw, if I leave that black hole long enough, eventually the black hole will just evaporate. There'll be nothing left but some radiation. And in 1975, Hawking claimed something really remarkable. He claimed that at that point, the information would have genuinely vanished in the universe. Not just it would be impossible to get in practice, but it just isn't there at all. There's no way to reverse the process and get it back. It's just gone. Quantum gravity, different from every other theory of physics, is just fundamentally not reversible. So in this talk, I'm going to try and explain to you a bit about what Hawking's argument was, and it was a very good argument. In Ahmed's talk next, he's going to explain to you why that argument is wrong, or at least, yeah, every physicist in this room thinks the argument is wrong. There's still a small number of people who would say maybe it's still right, but I think the overwhelming consensus at this point is it's wrong. And there's going to be a key player in both of those talks, which is quantum entanglement. So you've already seen that in Subir's talk. But I'm just going to say a bit about that from more of a sort of information theory point of view, whereas I think Subir was talking more from a sort of condensed matter, materials, physics sort of point of view. So here's a story you might have heard about quantum entanglement. Quantum entanglement lets you send information faster than the speed of light. I do something on one side of the universe, and an entangled particle, several galaxies away, is instantaneously affected. So this story, as I wrote it there, is wrong. The reason you can't send information using entangled particles is all you can do is measure one particle. And when you measure the particle, you get some random answer. And depending on the answer you get, that gives you information about the state of the other entangled particle and what measurements on that other entangled particle would see. But you can't control your measurements. So it's not something you can use to actually send a message. In fact, I can get something exactly the same as this in a very, very non-spooky way, just completely in classical physics. Let's suppose you take two balls. One of them is going to be red, one of them is going to be blue. You're going to hide each of them in the box. And then I come into the room after they've been put in the boxes, and I take one of the boxes. And I take that box and I fly off to Alpha Centauri. From my point of view, I don't know what the ball's color is going to be when I open my box and look inside. It could be either, 50% chance. But the moment I open it and I see that my ball is, say, red, I instantaneously know that if you open your box, then you'll see a blue ball. Okay, I know, that gives me instantaneous information. There's no speed of light delay or anything like that. The two states of the two balls are correlated. This is obviously very unremarkable, but the reason there's no magical faster than light communication going on. But the reason it's unremarkable is that the color of the ball was really determined before I ever left Earth, right? I didn't know what it was, but the universe did. The state of the universe had that well-defined answer for what I would see when I looked at it. So correlation in the classical physics requires you to have missing information, requires you to not know things about the state of the ball that then allows this correlation, non-local correlation, to happen. The claim of quantum entanglement is that in quantum mechanics, even if you know the state of the two balls perfectly, measurements can still be random, and you can have correlation between the measurements and the two distant balls, even from the perspective of someone who knows absolutely everything there is to know about the state. So Einstein sort of pointed this fact out in this paper with Podolsky and Rosen when he was at the Institute in 1935. And his answer to this was, okay, this must tell us that quantum mechanics is just incomplete as a description of nature. That quantum mechanics doesn't know what the measurement's going to look like when we do it, but there's some deeper, more meaningful theory that does know, that there's extra hidden information. And if you knew that hidden information, you'd know in advance what the measurement outcomes would be. This is a very satisfying answer. Unfortunately, it's not true. John Stuart Bell, a few decades later, pointed out that actually this only makes sense if you consider one set of measurements on each ball. In quantum mechanics, there's a whole infinite set of different measurements you can do, and all of them have different sort of correlations. And in fact, if you look at the complete set of all those correlations, they can't be explained by any sort of theory of hidden information where they were all determined in advance. And that's why they had correlation. So quantum entanglement is really, really, really weird. It's not sending information faster than light, but it's some sort of super correlation thing that's more than you could ever have in an ordinary classical universe. And it's also going to create something else that can't happen in the classical universe, which is it's going to make black holes glow. So let's see how that works. So everywhere around us, even if we're in total vacuum, there are quantum fields. Okay, there are electric fields, magnetic fields, you're probably familiar with. There are actually all sorts of other fields as well. But actually, for our purposes, those two are going to be the most important ones. And it turns out those fields, even in empty space, are all entangled with one another. Quantum vacuum state that's full of all this complicated stuff. In particular, that's true about the fields just outside the black hole horizon and the fields just inside the black hole horizon. They're entangled with each other. Short range entanglement. Throughout the universe, this is true, but it's true at the black hole horizon. The thing about a black hole horizon that's unlike any other point in the universe is that if we evolve over time, then the fields just outside the horizon are eventually able to escape and they radiate off to infinity. And meanwhile, the fields that were just inside the horizon, very, very close, are not able to escape. They just get stuck inside the black hole forever, no matter what they do. So what this means is that this short range entanglement that's just present all through empty space gets pulled apart into very long range entanglement between the inside of the black hole and some fields way out going off to infinity. This is what produces this noisy thermal radiation known as Hawking radiation. Okay, it's noisy because it's entangled with stuff inside. And if you want to have noise going off, then you need some energy to carry that noise, because if I have no energy, I can't transmit any information. This causes the black hole to begin to evaporate. So this Hawking radiation, as I say, is completely random. It's just noise because it's entangled with stuff inside the black hole. And it doesn't carry any information about something that had fallen into the black hole, my copy of Twilight, for example. But that's OK. That's totally normal so far, because it's entangled with the black hole. And we said that even if the quantum state overall is like known and well-defined and noiseless, then individual parts of it might not be, because you have entanglement. But now let's keep carrying on, going forwards in time, and we're going to see something weird. So as we go forwards in time, more and more of these noisy entangled particles are going to get emitted. One, all these like photons, all this radiation going out. And meanwhile, the black hole is getting smaller and smaller because it's losing energy. So eventually you get something like this. I was pretty lazy with my PowerPoint skills, so I only showed 4 of these fields getting emitted to infinity, but in fact, there's loads and loads and loads. And eventually you reach the point where the amount of radiation becomes bigger than the number of constituents of the black hole that Juan talked about, that is proportional to the area of this black hole horizon. So that's getting really quite small at this point. However, if the only source of this randomness, if the only reason that the radiation looks random is because it's entangled with the black hole, then the radiation should have the same amount of randomness as the black hole does. That's just how entanglement works. But Hawking's calculation says the radiation still looks just completely random. And if it's completely random, then the black hole needs to have more randomness than it has information describing its state. And that's obviously completely impossible. If I have a hard drive, right, the amount of randomness in the state of the hard drive is bounded by the amount of information the hard drive can carry. Even if it's in a totally random state, that controls how random it can be. And so at this point, there's only 2 options. The first is that information is lost. That's what Hawking said had to be true. He said, I've done this calculation. It shows that this radiation coming out is just completely random, and there's no way for that to be consistent with everything staying deterministic and reversible and the usual rules of the laws of physics. The second, of course, is that Hawking's calculation has to somehow be wrong. And I will now turn over to Ahmed to explain why that's the case.
Okay, thanks, Geoff. And thanks, Juan and Subir, for your very clear talks. It's clearly going to make my talk a lot easier. So what I'm going to talk about is the supposed resolution, well, not supposed, I believe it. So the resolution of the information paradox, this paradox that was found by Stephen Hawking roughly 45 years ago, and only a few years ago, we think we cracked it. The main player in the story is going to be these space-time wormholes, which are going to be the key in resolving the paradox. So as with everything at the Institute, everything begins with Einstein. And we know, everyone here knows that Einstein was smart. Einstein was also wise. And I found out just a year and a half ago or 2 years that Einstein was actually 6 feet tall. We had these signs everywhere over campus or around campus about keeping away from one another by 6 feet. So here Einstein is a unit of length. And there's something here about being too obsessed by something. I don't know what this says about the IS. And we also learned from Geoff's talk and the previous talks that Einstein was also wrong. He was wrong about a few things, and as discussed by Geoff, he was wrong in his understanding about quantum entanglement and how bad it is for physics. The upshot is that entanglement is merely some super form of correlation. It is not causation. One cannot use entanglement to send signals faster than light in some weird, crazy, spooky action at a distance way. Everything is still causal, and you need to wait for some time to get any message that is sent to you using entanglement or without. The thing that you get from considering entangled particles is randomness. And the main part of this talk will be about measuring and understanding randomness. So let's start with a very simple model, which is to consider, suppose you're given a computer program, which runs on this very old computer, which I was told might be more familiar with this audience. And suppose that this program, it either outputs the same definite number from 1 to 1,000, or it outputs a random number between 1 and 1,000. And you're tasked to determine which of the two programs it is. How would you do it? Well, it's pretty easy. All you have to do is run the program twice. If you run it twice and you get 2 different numbers, then you know with probability 1 that it's option B. It's a random number generator. But if you get the same answer, then with very high probability, you know that it has to be option A, that it's the definite program. Why? Because the chance of getting the same number in the random case is it's essentially 1 over 1,000. Okay, so that's good. It turns out that there's an equivalent way of formulating this way of measuring randomness in terms of instead of taking one computer and running the program twice, you can imagine having 2 computers and just running once. And then to ask the question of whether swapping the 2 computers results in the same numbers on the screens or different numbers on the screens. So if the swap is noticeable, meaning that the numbers are different, then you know with probability 1 that it's a random program. But if it's not noticeable, meaning that the numbers are the same, then you know it's going to be the not random program, the definite program. Okay. It turns out that this way is more, this way of phrasing the measurement is more useful for the case of black holes. So the question we want to ask, we want to apply this swap test to check whether the Hawking radiation is random or not. Here I have a picture of a black hole with some particles inside which are entangled with some outside Hawking radiation. This red line here is supposed to denote the entanglement. The first step is to consider a copy of this system. So here it is. The color coding is just so you keep track of what is what. So this is a copy. Again, it's a black hole with the same number of particles inside, entangled with particles outside. Let's run the swap test. What you need to do is we're checking if the radiation is random or not. So we need to swap the 2 radiations and then try to estimate, see whether this system is similar to this system or not. You can do this by eye in this picture. The similarity is small. They're very dissimilar. And hence the swap is noticeable, and so the radiation is random. Okay, so this we just did a calculation via diagrams to show that the Hawking radiation is random. This is essentially Hawking's observation. We just redid Hawking's calculation basically. The framework in which we did this calculation is that we considered quantum particles. That's the thing that gave us the Hawking radiation produced across the horizon, but without quantum gravity. Okay? We didn't say anything about quantum gravity yet. The reason why Hawking didn't consider quantum gravity was that he thought that the effects would be small and that they would remain small even as the black hole evaporates and shrinks. But perhaps one should expect that the quantum nature of gravity and space-time, that it might become important at some point, and in fact, that's going to be the punchline of this talk. And it's like maybe sort of in retrospect, maybe we shouldn't have been surprised that there was a problem because we're essentially throwing away half of the physics. We're saying that only particles are quantum, but space-time is not. You know, physics is not a salad bar. You don't get to pick one and leave the other. It's got to be quantum all the way. So we want to see how quantum gravity changes the answer, but we need to first answer the question of what is quantum gravity. So in my remaining time, I'm going to explain that. Before quantum gravity, let's talk about quantum particles. So a very beautiful formulation of quantum mechanics is due to Feynman through what's called the Feynman path integral of quantum mechanics. What this says is that if you have a particle that starts at position A and ends at position B, it is actually in a superposition of traveling along all possible paths from A and B. Should have noted that here's Feynman doing some acoustic physics. So that's normal quantum mechanics for particles. Stephen Hawking applied the same reasoning, but to space-time. And in so doing, defining something called the path integral of quantum gravity. What this says is that if you have a space-time, so let's say here's a space-time with 2 black holes, that when it evolves, it is also in a superposition of evolving in all possible ways. What I'm showing here is one possible way where nothing happens. It's a very boring evolution. The 2 black holes just remain the two black holes. But something else that can happen, a different path of the evolution, if you will, is that in some intermediate time, a space-time wormhole fluctuates into existence, connecting the two black holes and then disconnecting again. That's possible. But something that was observed only recently is that these wormholes do something very, very funny. Yes, they attach to the interiors and disconnect, but when they do so, they actually swap the two interiors to one another. So here we had red, red, then it became blue, red. But in this boring evolution, nothing changed. And Hawking is the one who taught us how to study quantum gravity using this path integral and so on. He knew all about wormholes, but he didn't know about this effect. And now let's revisit the swap test, but armed with wormholes. Here on the left, this is just a recap of Hawking's calculation back in '74. After you swap, you notice that you can notice a difference between these two pictures. At least I hope you can. And so the Hawking radiation, you conclude the Hawking radiation is random. 45 years after Hawking, in two papers in 2019, one with Juan Maldacena and I, and three collaborators, Hartman, Shaguli, and Tajdini, and also another paper by Penington and Stanford, Schenker, and Yang, we used these wormholes. We show that the fluctuation of these wormholes gives you a different answer. We do the same calculation. We swap the radiation. But then as a bonus, gravity does an automatic swap of the two interiors. So two swaps happened. The swap that you did by hand and the swap that was automatic by the black hole. And what that second swap does is that it cancels the swap that you did. And now if you look at these two pictures and you ignore the colors, these are essentially the same picture. You cannot notice that a swap happened, and hence you conclude that the radiation is not random. That's the essence of the argument. And so what this shows is that wormholes are an important ingredient for black holes to be consistent with what Geoff described as reversibility and information preservation. To me, this is an example of something that you see all over physics, which is physics has to be weird to be normal. Some notable examples of this is the stability of atoms. So I mean, we have atoms on this table and everywhere, and we sort of intuitively understand what they are. But in order for them to actually be sort of physically sensible, you need something as weird as quantum mechanics to justify their existence. And similarly, if you try to understand the physics of motion at very fast speeds, you need special relativity, which is also pretty weird. And similarly, for understanding gravity, you need general relativity. Before I end, let me say something about Einstein. So Einstein was worried about entanglement and action at a distance. And he would have worried about wormholes. The reason being is that you can do the following thing. You can imagine two black holes with their Hawking radiation. And if you collect the Hawking, and so you can do the following experiment. Imagine you throw a present into one of the black holes. And then you go into the radiation. There's a manipulation that you can do which can force the black holes to swap. You can force a wormhole to be generated that swaps the interiors. And this swapping relies heavily on the fact that there's entanglement. And once this happens, you can move the present from one black hole to the other black hole. Hence, it looks like the presence of entanglement, in addition to this manipulation that you do, it allows quantum gravity to perform some kind of action at a distance. Because you acted here, but then you move the present from there to there. And so in some sense, Einstein was right after all. And with that, let me end. Thank you.
Okay, now we can have some questions from the audience or also from the Zoom audience. I think someone is going to monitor the Zoom, so please shoot your questions. Why is the swap always on capitals? That's a question for you.
Just for emphasis.
Yeah.
I wonder, are these jets sometimes two-sided or always one-sided?
Well, I think in this particular case, it's supposed to be one-sided because that's the one that is coming to us, and then we don't see the other one.
I think we have very often we see two-sided black holes, I believe, or jets coming out of that.
Yeah, I guess that depends on the orientation. So, but if there's one coming to us and the other one going away, it's harder for us to see the one that goes away.
Do these comments inform how you look at dark energy and dark matter, those concepts?
No, not so far. So these are aspects of quantum gravity that are not directly related. Of course, in the future, we expect that by understanding black hole interiors, the singularity, we saw that in the interior of a black hole there is a collapsing universe. Maybe we'll be able to time reverse that and understand expanding universes, and eventually understand why the universe we have, how the universe we start, how the universe we know we live in started, and because it had a singularity in the past, and we need to understand that. And perhaps understanding that will help us understand dark energy, but it's a longer time project.
You've written at least one paper talking about potential wormholes effects in cosmology, right? Yeah, but it's pretty mysterious still.
Yeah.
Juan, when we're talking about the level of wormholes, does the idea of distance make sense? So when we're talking action at a distance, maybe the distance itself loses its meaning.
That's a fair point. So if you noticed, I had an asterisk when I said action at a distance. So in some sense, by the creation of the wormhole, going from one black hole to the other, you've already bridged that distance. So in some sense that maybe there's not a distance anymore.
I mean,
yeah, continuing this in your calculation. Thanks. In the explanation why the wormhole sort of spoils the swap of the two black holes. This is only one path in the path integral. Of course, there is another path that nothing happened, and there are many possible paths. For the argument to be successful, it has to be that the wormhole effect takes place most of the time. Is it true?
Yes. So you essentially, well, in the calculation of the entropy or the calculation of the randomness, there are many contributions and they're weighted differently. It turns out that the wormhole contribution, well, it depends on which phase of the black hole evaporation you're in. At the relevant times, you find that the wormhole contribution dominates.
And the swapping effect.
That's what I mean. Yeah.
Yep.
The issue of that information cannot be destroyed was brought up. I'm not versed on information theory, but is there something like potential information? Like we talk about potential energy. Is there something like potential information?
I guess I should try to answer that. There's information you don't know yet, I guess, would maybe be something like that. I see. Yes, so I guess the question is, with energy, to see that energy was conserved, we had to take into account new forms of energy that we maybe wouldn't have thought about before that. I guess the same thing is true here, because there's the sort of simple, accessible information, words in a book you can easily see. But to really see information be conserved, you have to consider all possible forms of information, including very, very complex, subtle details of the state. Sort of, you have the macroscopic properties of your state, things like the temperature and the pressure and so on, and that's a sort of simple sort of information. But then there's much more detailed sorts of information, the specific details of particles and where they are and their speeds and so on. And so that's a much less accessible sort of information. So you could think of that as being like potential information, I guess.
You also have the notion of a system that has not completely thermalized, for example. So if it's completely thermalized, it contains no information, but if it's on the way there, there's still some information in it. So maybe that's one way to answer your question, I would say.
I was wondering along the same lines as Avi regarding these path integrals. But my question is, so for you to be sure that your calculation is correct, you have to know all the effects. So Hawking wasn't aware of the wormhole. Is it possible that there's effects that are you're viewing as like canceling each other out? So you're just kind of assuming they're not there. Do you allow for the possibility, I'm with you by the way, but do you allow for the possibility that there could be effects that we don't know about yet that could affect these calculations?
The path integral of quantum gravity is a wild, wild beast. Nobody really understands it completely. What we managed to do was to identify contributions that we can actually analyze in a controlled manner, which miraculously gives us the answer that we were expecting on the nose.
I should say there are very simple models, so one dimension of space and one of time, where you can do the path integral exactly and completely and see that this is indeed the dominant thing. But we don't live in one dimension of space and one dimension of time, so that's not a completely satisfying answer.
I was going to say exactly the same thing, yeah. And of course, and I gave you an example of a simple situation where that was true.
I'm speaking from ignorance here, but it does seem to me like the question before, or the comment before, that wormholes undermine the concept and perhaps the fact of space has impacts for most of your speculations and most of your conclusions. So I wonder if you'd return, or any one of you would return to that and just tease that out a little bit more, because that seems like a major qualification in most of what you said.
I can say one quick comment and then I'll pass it on to the other panelists. So the thing that you can try to do is, assume wormholes, assume that, put them in your theory and try to find contradictions that are caused by the presence of the wormholes. Some like closed time-like curves. Can you go backwards in time and kill your grandfather, and so on and so forth? At least in my analysis, I haven't been able to find any of that sort of problems. But maybe other panelists have something else to say.
Maybe I can mention here. So I mentioned this idea of duality, that you could think in terms of wormholes and the path integral of quantum gravity, the way Hawking was performing it. But there's a dual description in terms of a quantum computer of a bunch of qubits that are interacting with each other. And there the computations are very, very different. And in these simple cases, you can actually carry them out in a very different language that's much more intuitive to, at least to me. And you end up getting similar results. So then it gives you some confidence that since you have these two very different ways of computing the same thing, and they give the same result, it gives you some confidence that these flights of fancy into wormholes actually mean something.
Yeah, I think in some sense you're right that the space-time loses some meaning. So normally we think of in classical general relativity, space-time is some construct that tells us the distances between different points. And the idea is that in quantum gravity, that's intimately connected with something, this quantity called entanglement. So in the ordinary description, so points that are distant are less entangled. But the idea is that when you start having more quantum entanglement, things start getting closer in some way. And so there might be a little wormhole that connects them and brings them closer. And so somehow the idea is that perhaps this entanglement is more fundamental, and that will, once we have the full quantum description, there's only quantum mechanics and so on, and we'll find points in space-time as properties of the entanglement of this complicated quantum state. And so points that will be close are points that are highly entangled and so on.
About the black hole firewall and what's the current status of that issue?
So sorry about the firewall. So as Geoff described, the source of the information paradox comes from the fact that you have these entangled particles across the event horizon of the black hole. The assumption that led to that is to say that the event horizon is a smooth patch of space-time. There's vacuum there. There's nothing special in that location. So in the firewall discussion, we were saying that one possible resolution of the information paradox is to simply break that entanglement between the particles inside and the particles outside. But if you break the entanglement, well, you won't have the information paradox anymore. But if you break the entanglement, you also won't have the vacuum, the smooth patch of space-time at the horizon. And if that's true, it would, well, radically change our picture of what a black hole looks like, and in particular, put into question of whether there's an interior to the black hole.
We could definitely spend the entire night here together. And that's the point. This is what was so magnificent about this panel, about this problem, and about the kind of work I think the IS produces. So I want to thank Juan, Subir, Geoff, and Ahmed, and I want to thank you all. And let's all applaud.